We're going to begin a consideration of objects that have real size. Up to this point, we treated everything pretty much like a perfect little geometric point size object. Once you have objects with real size, though, you have to consider things like rotations and deformations. And here we're going to begin getting into the rotations. Let's suppose that we have an object, kind of a little bit of potato shape or something there, and we sketch on the object a little reference line. Maybe get away with calling that the RL. The reference line that helps us to see how the object is oriented. We have an axis of rotation. We are only going to consider fixed axes, that is, each axis is held in place. It's not itself allowed to roam around. And let's suppose that the object is going to rotate. Maybe it'll rotate around in the counterclockwise sense. So here, made it a little bit easier. I've already redrawn the object and it's rotated a little bit. Here in red, that's the original reference line, or you can think of it as the positive x-axis. And now the new position of the object can be described by this angle, theta. And in fact, theta really is just our old idea of a rotation angle. But in this context, theta is the angular position of the object. Also, as we discuss this, there are going to be terms that nearly duplicate what we have done before. There's angular position. Well, there was old position. There's going to be angular velocity. There was our old velocity. But if you need a word to describe it, something that's better than saying the old velocity, the word linear works well. So here, for the new quantities, we would either say angular or rotational, something to that effect. With the old quantities, often the words linear or translational are used, although I may still refer to the old velocity or regular velocity or something to that effect. All right, so theta, back to this, is the angular position. Again, theta is really just our regular rotation angle, so the old rules apply. Counterclockwise motion, that's the positive direction. Clockwise motion is the negative direction. Let's consider our object again. This time it's rotated around a little bit further. In black is the last version that we saw. Now if it's rotated around further, the red is the new position of the object. And now this change in the angle is going to be delta theta. In keeping with the way we usually use delta, that means it's the final minus the initial. It's the final angular position minus the initial angular position for the object. But this is going to be the angular displacement. Our old displacement or linear displacement would have been a delta x or a delta y or a delta r, perhaps, depending on exactly what we were looking at. So we can describe the position of an object. We can describe how the object has changed in a rotational sense, but we probably also want to know how fast it's spinning around. There we're going to get into speed or velocity. So let's do that very quickly. We're going to have angular velocity And the common symbol for that is a lowercase Greek omega. And the omega, its average value is going to be the change in the angular position of the object divided by the elapsed time, or the instantaneous angular velocity is going to be, kind of have to go back to chapter 2 and compare to that. It's going to be the limit as the elapsed time approaches 0. Kind of says do the experiment as quickly as possible of the angular displacement divided by the elapsed time. Omega can be positive or negative. If omega, the angular velocity, is positive, then the object is rotating around counterclockwise. If the omega is negative, then the object is rotating around clockwise. And if the omega is 0, then I guess the object's not rotating at all. The rate at which it's speeding up or slowing down in a rotational sense is going to be the angular acceleration. And here, well, lowercase Greek alpha is a common symbol for angular acceleration. And here we're going to have the average angular acceleration is equal to the change in the angular velocity divided by the elapsed time. Or if we want the instantaneous angular acceleration, that's going to equal this limiting idea once again. Might be nice to get one more equation out of this. So these are really definitions, but if omega is constant, then, well, constant angular velocity, so it's really not speeding up or slowing down, it's continuing at the same rate. And if that's the case, then the average value of the angular velocity, no matter how you measure that, it's going to be the same as the instantaneous angular velocity whenever you measure that. And substituting, doing a little bit of work, this just parallels what we did in chapter 2 once upon a time with linear velocity and whatnot. Then we can derive the equation that the angular displacement is going to be the angular velocity times the time. Here, just letting t represent the elapsed time, as we have done before. Or, well, second way to write this would be to expand the delta theta to the theta final minus the theta initial and rewrite. And that's going to give that the theta final is the theta initial plus the omega t. And I imagine in a later section I'm going to summarize all of the equations, write them together so that we have a good look at what's going on. With the discussion of angular quantities, it actually becomes very useful to think about, well, what are we going to use to measure the angles? Degrees is the obvious answer, but if you get further into it, you actually just kind of find that degrees are cumbersome. Let's see if we can get rid of some of what's here. Trying. There we go. And discuss units of measure for angular quantities. Degrees certainly have their place, but if you do a lot of work with angular quantities, it's actually going to be radians that perhaps are most useful. We're also going to consider revolutions, and we'll have to be able to change back and forth between all of those. If we consider, so here's a little motivation for this. Let's suppose that we have a circle. It's almost a circle. Let's suppose we have a circle, maybe slightly better. Center of the circle, and let's consider a sector where the central angle is delta theta, radius of the circle is r, and the length of this arc we're going to call delta s. And if we're using degrees, well, if we look at the delta s and compare it to the entire circumference of the circle, that's going to be in the same proportion as the central angle compared to the angle measure going all the way around the circle. And if we're doing this in degrees, that'll be divided by 360. So here we're considering degrees. And the delta S compared to the circumference, well, circumference is 2 pi r will equal delta theta over 360. And the delta S, multiplying by 2 pi r, rearranging a little bit, we can write this as 2 pi over 360 times the radius times the angular displacement. That equation certainly works, is certainly valid. However, again, if you do a lot of work with this, it just becomes a little bit cumbersome. There is another angle measure. Who says that going around a circle has to be 360 of something? It's much more convenient for many mathematical purposes to come up with a new angle measure where going all the way around a circle instead of 360 is actually 2 pi. Then if we look at this equation, the 360 in this work would be replaced with 2 pi, and the 2 pi in the numerator, the 2 pi in the denominator would cancel out, and we'd actually end up with a much simpler equation. So we're going to introduce the idea of radians. And it's an angle measure such that a complete circle is 2 pi instead of, like with degrees, where it's 360. And if that's the case, well, we could actually repeat the work that's up here. Let's give that a try very quickly. We're going to set up the ratios once again, the proportion, and we're going to have that the delta S compared to going all the way around the circle, that's the delta S compared to the circumference of the circle, is going to be the same as the angle measure there, the displacement, the delta theta, compared to the angle going all the way around a circle, but in radians, that's going to be 2 pi. And then the delta S over the circumference is 2 pi r. It's going to equal delta theta over 2 pi. And if we solve for the delta S, we'll end up with, well, multiply both sides by 2 pi r. The 2 pi's cancel out, and we're left simply with r delta theta. That's a good equation. We're going to make more formal use of it in another section, but this is just intended to introduce the idea of radians and how useful they can be. Make the comparison. If you had to do a lot of work with this, would you rather use the equation up here that involves the 360, or would you rather use the equation down here that does not? It's much simpler. It's almost a no-brainer, I hope. However, anytime we write an equation like this, we have to remember that radians are required. In fact, there is, I mentioned revolutions, that's another angle measure that gets used often. And going all the way around a circle one time is 1 revolution. So we can make a connection between these 3 different angle measures. Going all the way around a circle on the one hand is 1 revolution. And that's the same as 360 degrees. And here it's really convenient for thinking about unit measures and changing units and whatnot, unit conversions. It's really more useful to write DEG for degrees as opposed to the degree symbol. So 360 degrees works in many contexts, but it's really better here to write out the degrees, at least in my opinion. Also now, going around a circle one time is 1 revolution, but that's the same as 2 pi radians. And we can connect these in a third equation if we like. So going around the circle one time is 360 degrees, but that's the same as 2 pi radians. Or if we prefer, divide both sides by 2. Think about a half circle, and you have 180 degrees is the same as pi radians. And then we can do unit conversions. Although, to be fully honest, angle measures are not considered units exactly. They're actually called pseudo units. Maybe is one word. So instead of doing unit conversions, maybe we're really doing pseudo unit conversions. But it turns out that the method really is the same. So we could do just one quick example. Suppose that we wanted to convert 30 degrees to radians. Well, got to go back and do a conversion here. Let's think fraction. So if it's 30 degrees, we can put that over 1. We're going to multiply by the conversion factor, which is really the number 1, just in disguise. This is cross-cancellation method. Here, if I have degrees in the numerator, then here I want degrees in the denominator, and that leaves a blank for the thing that I'm changing to radians. And then just put in the numbers that make the correct connection between radians and degrees. And we had that pi radians is, that's half of the circle, is 180 degrees. The degrees cancel, and the 30 and the 180 will cancel down, leave 60 in the denominator, I believe. And this would be pi 6 radians. And that's great for a math class. Math classes often like to give the angle measures in terms of pi, but this is science class, so we might go a step further and say that that's about 0.524. I should keep more decimal places, but about 0.524 radians. We'll make use of the radians in later sections, but I hope that's a good introduction to it. This has been a long section. Try to make the others go a little bit faster.